Today's goal of this lecture. Today I will say just basic topic. Today I will say different open ball in metric space, because we all of us know in Rn there exist different type of metric space. So notice at first the different type of metric. This is the D1 matrix, means standard metric or usual metric on the space R. This is called Euclidean metric. Here I have considered it not Rn. Here I have considered n equal to 2. So this is the D2 metric. And when this is p to the power 1 over p, then this would be dp matrix. And when n equal to infinity, then this is the supremum matrix. We all of us know this type of matrix, and this is called the discrete metric, and this is called the bounded metric. And last, this is called the induced metric. We all of us know this type of matrix. Today I will say open ball in different metric space, because in different metric space open ball would be different. Because actually today's goal of this lecture, today I will see topological space. We all of us know topological space is collection of open set in the space X. This is denoted as U subset of X, such that U is open in X. And in topological space, this collection of open set is equal to actually tau. Then option 1, topological space means phi and x always belongs to tau. Option and 2, the criteria 2, if U belongs to tau, then arbitrary union of open set is an open set. Third, if U1, U2, Un belongs to tau, then finite union of open set is an open set. And we all of us know topological space. If X be a topological space, in topological space, open set mean this is if the topological space constructed by which member, this is actually the open set. So in topological space open set is different and very easy. We say that a subset U of the topological space is an open set if U belongs to collection of this tau. Because always topological space be the member of open set. So when X to be metric space, then tau equal to the collection of the D open set. This is actually the metric topology. So open ball, which is open set in the metric space, which varies in metric space, in different metric space, the open ball is different. So today's goal of this lecture, today I will see such type of open ball which are different in different metric space. This is today's goal of this lecture. When n equal to 1, then in standard metric space D1 it would be such types. Since here I have considered n equal to 2, so D1 metric space would be absolute value of x minus u plus y minus v. So the open ball, here the point 0, 0 and the radius r equal to 1 would be xy belongs to R2, such that absolute value of x, since here the point is 0, 0, u and v is 0, 0, so absolute value x plus absolute value of y less than 1. And the picture would be notice when xy greater than 0, then this would be x plus y less than 1. When xy second coordinate, then this would be minus x plus y less than 1, and when xy third coordinate, then this would be x minus y less than 1. In fourth, minus x minus y less than 1. So the picture would be just like a cube. This picture would be such type. Here 1 0, here minus 1 0, here 0 comma minus 1, and here 0 comma 1. Picture would be such like of cube. This is the open ball in D1 metric space when n equal to 2. D2xy with the center 0 0 is summation I equal to 1 to n xi minus yi whole square to the power half. This is the D2xy, and if we consider the metric space D2xy and 0 0 is defined as, obviously we all of us know, I equal to 1 to n x modulus xi minus yi whole square to the power half, because here I have considered it n equal to 2. Then b d2 0 0 with respect to the radius 1 would be xy belongs to R2 such that x square plus y square less than 1. This is actually the circle of radius 1. This is the center 0 0 and this is the radius 1. Then if we consider the submetric, means d infinity, and when n equal to infinity, then this is defined as maximum of xi minus yi, where I lies between 1 to n. Therefore, since here I have considered R2, therefore submetric in R2 such type x1 y1 comma x2 y2, this is equal to maximum of absolute value of x1 minus x2 comma y1 minus y2. Therefore b infinity with respect to the center 0 0 and radius 1 is maximum of absolute value of x1 comma absolute value of y1 less than 1, and the picture would be when that imply modulus of x1 less than 1 and modulus of y1 less than 1, then the picture would be such type. Here the center 0 0, this is y1 equal to 1 and this is y1 equal to minus 1. This is x1 equal to 1 and this is x1 equal to minus 1. Therefore, the picture would be this square. The open ball in D infinity metric space would be such type. I hope my all viewers have understood clearly. Okay? Well. And A subset U, who is contained in the metric space, is open in this space if given x belongs to U, there exists r greater than the 0 such that this open ball contained in this U. Then we can tell the subset U is an open set. If D1, D2 be two metric space on the set X, then a set U which contain in X may be open in this space or may not be open in X. A set U is not open set if there exists X belongs to U and for any R greater than 0. If B of XR does not contain in the set U, then we can tell the set U is not open set. Now I will see how look like the open ball in discrete metric space. Consider D equal to discrete metric space and open ball look like B of XR equal to Y in X such that D of XY less than R. Then 0 less than R less than equal to 1. When R less than equal to 1, then the open ball look like Y in X D of XY less than 1. And D of XY less than 1 means obviously D of in discrete metric space when D of XY less than 1, then D of XY equal to 0, that imply X equal to Y. Because we all of us know definition of discrete metric space. And then when R less than equal to 1, then this implies singleton set X. And when R greater than 1, then B of X are equal to whole space X. And A set U be any subset of X. And for any point X in U, B of X comma half is always B. If we consider this type of open ball, B of X comma half in discrete metric space, this is actually singleton point X. Thus U is an open set. And since open ball contain in the set, so obviously the set U is open. Thus any subset X in open with respect to discrete metric space, because in discrete metric space open ball look like only singleton set X. Now consider X equal to C01. Now the submatrix in this C01 is D infinity F comma G equal to supremum X belongs to 0 1 D fx minus gx, and this is the D infinity metric we all of us know in C01. Now my question, how look like the ball, open ball in this metric space? Here B of F comma R is set of G belongs to C01 such that supremum of X belongs to 0 1 fx minus gx less than R, and the picture would be such type. Consider this is the f function and this is the interval 0 1, and this is the f plus minus R and this is the f plus R, and here G with the such function in C01 whose distance would be less than R. So consider obviously G function would be lie in this boundary, so consider this is the G function. This is the G function. Then what would be f minus G? F minus G would be, this is the f function and this is the G function, then f minus G would be such type. This is the f minus G. But here absolute value of fx minus gx. So since this is the absolute value, so this value always would be positive. So f minus g would be such type. And this absolute value, absolute of supremum of this absolute value less than R. That means this supremum value always would be lie in this boundary. And this is the ball in the submetric in C01. I hope my all viewers have understood. As for example, consider x equal to C01 under the sup norm. Obviously sup norm means, sup norm of f means supremum of f of t where t belongs to 0 1. Then draw the open ball in this subnorm. Then consider B01 equal to set of those function f in x such that d infinity f comma 0 equal less than 1. This is the interval 0 comma 1, and d infinity means obviously d infinity matrix defined as norm of f minus 0 infinity less than 1, that means f in x such that norm of f infinity less than 1. And norm of f infinity means obviously supremum of f of t where t belongs to close 0 1 less than 1. That means f in x such that absolute value of f of t less than 1. Therefore, supremum of f of t less than 1, that imply since supremum value less than 1, that means absolute value of f always would be less than 1. That means if we consider this is y equal to 1 and this is the interval y equal to minus 1, then f function always lies between this interval. Therefore, B01 represent a set of continuous function on the closed interval 0 1 which are bounded by y equal to minus 1 and y equal to plus 1. Now in C01 consider the D1 metric. We all of us know C01 D1 matrix is integration of f of t minus g of t. That means we all of us know integration means the area bounded by f of t minus g of t. That means since D1 is such type of, then norm of f1, here I have considered only norm of f1, that means g function is here equal to 0. Then this would be integration 0 to 1 f of t dt. Now draw the open ball B01 in this norm. Obviously B01 would be such f in x such that d1 f of 0 comma 1 less than 1, and d1 f of 0 comma 1 less than 1 means f in x such that norm of f minus 0 1 less than 1. That means f in x such that norm of f of 1 less than 1, and norm is less than 1 means integration 0 to 1 absolute value of f of t dt less than 1. Here f of t dt less than 1 absolute value. That means if we consider this type of function, absolute value means this value also would be in positive part. As for example, we all of us know this is the sin x in 0 to 2 pi. We all of us know integration 0 to 2 pi sin x dx equal to 0. But integration 0 to 2 pi mod sin x dx, this value is 2. So mod means here only positive part. F be in x such that integration 0 to 1 mod or modulus of f of t dt less than 1. Therefore, B01 is a collection of continuous function on the interval 0 1 such that area bounded by the function f and the x-axis, because integration means we all of us know this is actually the area. Therefore, B01 is actually the collection of continuous function on 0 1 such that area bounded by f and x-axis. I hope my all viewers have understood this is okay. Now I will see how look like the open ball in product matrix space. We all of us know product matrix space. Here the open ball look like, let x d1 and y d2 be matrix space, and D be the product matrix on x cross y. And for xy belongs to x cross y and r greater than 0, B of x comma y, xy comma r is equal to B d1 x1 comma r cross B d2 y cross r. As for example, let UB belongs to B of xy comma r, where U belongs to B d1 xy x comma r and V belongs to B d2 y cross y comma r. Consider this is the B d1 x comma r and this is the B d2 y comma r, and this vertical line is B d1 x comma r cross y, and this horizontal line is x cross B d2 y cross y comma r. Then obviously this part belongs to in the product matrix, and the ball here B of x comma y comma r, which is equal to B d1 x comma r cross B d2 y comma r. And if UV belongs to this ball, that means U belongs to B d1 x comma r and V belongs to B d2 y comma r. As for example, consider x1 equal to r, and in r consider the usual metric d1 xy equal to absolute value of x minus y, and x2 equal to r, and here consider the discrete metric d2 xy equal to 1 when x not equal to y and 0 when x equal to y. Now consider the product matrix x equal to product matrix denoted as product I equal to 1 to 2 xi, that equal to x1 cross x2. That means this is the set of x1 comma x2 such that x1 belongs to capital X1 and x2 belongs to capital X2. And let x equal to x1 comma x2 and y equal to y1 comma y2 on this product space x1 cross x2. Then d of xy equal to, consider on this product space d of xy, consider this Euclidean matrix I equal to 1 to 2 di xi whole square to the power half, since here I have considered n equal to 2, and that means this is equal to square root of d1 x1 y1 whole square plus d2 x2 y2 whole square root. As for example, consider x equal to 1 comma half and y equal to half comma 2. Then d of xy equal to square root of d1 1 comma half whole square plus d2 half comma 2 whole square, and d1 1 comma half whole square means, notice this is the usual metric, that means this is equal to 1 minus half whole square plus d2 half comma 2 whole square means d2 here the discrete matrix, so when x not equal to y then the value is 1, so this would be 1 square, then this would be square root of 1 over 4 plus 1, this means this is equal to square root of 5 over 4, and this is the product matrix in this space where d1 is usual metric and d2 is the discrete metric. If we consider this type of metric in product matrix space d dash xy equal to maximum of d I xi yi, where I equal to 1 to 1 2, then for this xy d dash 1 comma half and half comma 2, maximum, this is equal to maximum of d1 1 comma half comma d2 half comma 2, and maximum of d1 1 comma half means this is the usual metric, and this distance also would be half, and d2 means this is the discrete metric, so this value would be 1, and this maximum value is 1. That means for this metric, the value of product metric space at this point would be 1, and for this metric same point, but for this metric the value of product space is square root of 5/4. I hope my all viewers have understood geometrically what is the product metric, what is the geometry. Okay, well. Our new space, I will see the open ball in subspace metric space. We all of us know subspace metric space is, let XD be a metric space and Y be subset of S. Then the mapping which is defined from Y cross Y to R such that dyx comma y equal to d of xy for all xy belongs to X. Then we can tell this is the induced metric on Y, and y dy is called relative metric or induced metric, where y be subset of X, but d of y xy equal to d of xy. This is the induced metric we all of us know. Therefore, let y dy be subspace of a metric space XD, and if A belongs to Y and R greater than 0, then B of R dash A equal to B of RA intersection Y, where B of R dash A and B of RA are open ball of Y and X respectively. This is the open ball of subspace metric space. In subspace metric space, the open ball in y dy is look like B of R dash A equal to B of RA intersection Y. If we consider here A, therefore, if this is the B of RA, then B of RA intersection Y, this part be the open ball in subspace metric space. In metric space, this is known as subspace metric space, and in topology, this collection is known as subspace topology. Here not metric space. Here we have defined the subspace topology. So same notation. Here since I have considered X tau be topological space, so U belongs to tau, and this is called the subspace topology on Y. As for example, closed zero open half is open set in the set closed interval 0, 1, but not open set in usual metric space. We all of us know. Why? This is open in this subspace topology where 0, 1 is the subset of R, because we can write 0 half equal to in the closed interval 0, 1 intersection minus 1 to half. Since this is open set in R, so we can tell closed 0 open half, this is open in the set 0, 1. In the subspace metric space, this is open. Similarly half 1 is open in the set closed 0, 1, because in the subspace metric space, we can write half 1 as closed interval 0, 1 intersection half 2, and this is open set of real number, so we can tell this is also open in closed interval 0, 1. I hope my all viewers have understood how look like the open ball in subspace topology, Actually, subspace topology and subspace metric space are same. Subspace topology is higher dimension. Here U belongs to tau, and in metric space here U belongs to X. Since I have considered it X equal to R, which is usual metric, so usual topology and usual metric here equivalent. And consider the subset Y equal to integer. That means the picture would be such type. This is n, this is n plus 1, this is n minus 1, this is n plus 2, n minus 2, so on. Picture would be such type. Now, if 0 less than epsilon lies 0 less than 1, where epsilon equal to half, then if we consider such type of ball, n minus epsilon to n plus epsilon, if epsilon equal to half, consider u equal to n minus half comma n plus half. Then if we consider such type of open interval, here I have considered epsilon equal to half. We can choose similarly epsilon equal to 1/3, 1/4, and this intersection would be always singleton set n. And since this is open set in real number, so we can tell the subspace topology of subspace metric when Y equal to Z, subspace metric or subspace topology on Z is actually discrete metric. I hope my all viewers have understood this is okay. I will stop here, but I will hardly recommend you please see today's video with pay attention, because this part actually basic part for metric space, also higher dimension of topology. If you have any queries about this part, then do comment in comment box. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.